Hello, everyone. Today, I'm going to present to you our work about optimal condition training for target source operation. My name is Efthymios Zenis, and this is a joint work with Gordon Wichern, Paris Maragdis, and Jonathan Leroux. So the general task of audio source operation is effectively when we have the co-occurrence of multiple sounds inside the mixture, and one wants to reconstruct the independent sources. When we want to reconstruct all of the sources inside the mixture, we usually call this problem unconditional separation, whereas if we have some other information or to condition the system, we can call this problem conditional or target source separation. So we focus on this setup with multi-condition networks, as we see here. One of the prior works in this multi-condition separation frameworks is called heterogeneous target source separation, where we can see here that we can use different or heterogeneous condition concepts in order to target, let's say, the first speaker inside the room. So we can have this kind of target speaker by querying the network to reconstruct the female or the speaker who is the closest distance from the microphone, or the speaker who speaks French. So instead of performing permutation invariant training that we use conventionally in the unconditional separation training, we generate a mixture from a set of sources. And what we do is that for this kind of target waveform, we sample a discriminative concept which is associated with this target waveform. And what we do is that we backpropagate the error by using this kind of sampled discriminative concept, and we update the parameters of our conditional separation network. So one of the contributions of our paper is, first of all, to expand this heterogeneous separation framework for universal sound separation. So we have more general attributes than just speaker characteristics as we had before. So, for example, we can ask the network to reconstruct the most harmonic or the most percussive waveform, or, for example, the higher energy one, or the source that appears second in order in terms of time. And the freest way to describe sounds in general, which is querying using natural language, like I want to separate the dog barking. So instead of having this heterogeneous condition training where we have the set of available condition vectors and we sample one of these conditions to backpropagate the error, our method is called optimal condition training. And what we do is that first we perform an inference step using all these available condition vectors. We find the maximally performing one with respect to reconstructing the target waveform, and we update the model parameters using that. We also provide a refined way of performing optimal condition training, especially for cases where we focus on one condition vector. Let's say we have this kind of fixed condition vector. And what we do is that we also try to refine this, this input vector and make it look closer to the optimal or the ideal one for this conditional separation task. You can see more in the paper if you're interested, but effectively we use a conditional pseudo-MRF as our separation network, where we gradually modulate the input signal using several film layers. So we're going to see why this is really important using the different conditions. We have conducted our experiment using FSD50K, and we have here different partitions using sources in the mixture which are drawn from random classes out of the 200 classes available. Or, for example, we force these classes to be drawn from different superclasses. Or the hardest case, which effectively is when we force an intra-superclass separation framework, which effectively we say whether to reconstruct the acoustic guitar from a mixture of acoustic guitar and electric guitar, for example. So we see here that there are some conditions such as harmonicity and source order, which perform pretty good for all these partitions, but there are other single condition models, let's say this one, condition on energy, which fail miserably, mainly because near 0 dB, it's really hard to say which source is the highest energy one. For the most general way of describing sounds, which is text-based description, we see that although for random classes it performs really well, for the hardest case of extracting, let's say, the electrical guitar from the acoustic guitar, we see that the text-based description is not that well, mainly because those embeddings are really close to each other. The final thing that we want to see is why we do get this performance boost is the OCT Oracle, which is a model which is trained and evaluated with the best or the maximally performing condition, yields a higher upper bound in conditional separation, even compared against the Oracle ensemble of all these single condition models. So that means this extra information which comes in for free from our metadata from different conditions helps us understand how to perform this conditional separation better. Focusing only on text-based separation, we see the performance of Oracle optimal condition training and the Oracle unconditional permutation variant training compared to the previous state-of-the-art text-based separation. We see what we can do with our model using the heterogeneous condition training setup, which is like a little bit better than that. But we can see that we can obtain state-of-the-art results for text-based sound separation by just focusing on these updates using our the optimal condition training. And we can also do a little bit better than that by using our refining embedding mechanism, as we see here. Those results also hold for more difficult scenarios where we have sources drawn from the same superclass. However, we have this kind of performance gap. So we do have more results in the paper if you're interested. So I would like to thank you for attending the video, and I would be happy to see everyone in the Q&A session of ICASP. Thanks.